Just Miller Arts on College Physics. We are going to look at some more impulse and change in momentum, but now we're going to consider a force that varies with respect to time. So let us just get to it. Impulse due to a varying force. What we will have the impulse now has to add up the changing force over the time interval which is under consideration. So for this, that invokes some integration. We've got some t initial to some t final of some f of t dt. That is how we will define, or how we do define, impulse due to a varying force. Add up the contributions of the changing force with the time interval under consideration. So let us take a look at this. Consider a net force that is varying. Well, we will have that the impulse, should be a hat there, impulse is equal to some t initial, integral from t initial to t final. Now we have a net force as a function of time times a dt. Well, what can we do with this? Well, let's see. We still know that the net force produces an acceleration. Just if the net force is varying with respect to time, the acceleration is varying with respect to time as well. So we can still expand this out and say that this is equivalent to the integral from t initial to t final of m times a of t dt. That's a little hat on there. That's good. And there we go. Now it's a matter of, can we do something with this? And the answer is, of course we can, because we know the definition of acceleration. A hat itself is defined as dv hat by dt. That's the definition of acceleration, right? The rate at which velocity changes with respect to time. So let's stick this in here and see what we get. Well, now we've got that the impulse is equal to the integral. I'm not going to put in the limits yet. We've got an m dv hat by dt times a dt. Well, we could still say that we have this from t initial to t final, but it looks like we're going to change our limits of integration here, doesn't it? Because those dt's are going to cancel out. So I'm just going to go ahead and take this and note that those dt's go away, and we are left with the integral of m dv hat. Well, at t initial, the object will have some initial velocity. At t final, the object will have some final velocity. So we've got this going from v initial to v final. Let's change the limits of our integration there. And well, what does this give us? We're just integrating m dv. Whew, that seems like an easy integral, right? Well, that is just going to be equal to m times v hat evaluated from v initial to v final. Hat. So what does that give us? That's right. mv final hat minus mv initial hat. Does that look familiar? I hope so, because that's the same thing that we got when we considered a constant net force. It all works out the same, which ultimately demonstrates to us that it doesn't matter whether the force is constant, net force is constant, or varying with respect to time. The impulse due to a net force produces an object's change in momentum, because this is p final hat minus p initial hat, which is equal to delta p hat. So from all of this, one has the ability of defining a net force that's varying or non-varying in terms of the time rate of change of momentum. We can define net force as the rate at which momentum varies with respect to time. This comes up from here. Integrate both sides, we get a delta p, and we get ourselves impulse. So this is actually how Newton was first representing what a net force does. Net force produces a change in momentum over some time interval. Rate of change of momentum. But that's kind of that. So the main thing is that we still get impulse due to a net force produces an object's change in momentum, whether we have constant or varying net force. So let's do a little problem with this and see what we can do. Take some varying force. We'll take a simple model here. Just kind of go with this. So let us take ourselves a mass of 1.2 kilograms. We'll take ourselves a force that varies with respect to time, net force, that varies with respect to time, that we're going to say is 400 t minus 800 t squared with proper SI units, so this all works out to be force, not worried about those. And we're going to say that t goes from 0 to 0.5 seconds. So over that time interval, this force acts on some object with a mass of 1.2 kilograms. And we want to ask some questions about it, like, hey, what is the impulse? What's the change in momentum? What's the object's final velocity? What's the average force that acted? Those are all some good things to be asking here. Let's just start off with a part A. What is the impulse delivered by this net force over that time interval? I hat is equal to, well, this should be I hat direction. So I hat is going to be equal to the integral over the time interval from t equals 0 to t equals 0.5 seconds of the quantity of 400 t minus 800 t squared dt, and this all is I hat in here. I guess we could go ahead and stick that in. I hat at the end. We know that if net force is in the I hat direction, this is going to be in I hat direction. So we'll kind of just work with magnitude till the end, stick I hat back in. It should be satisfying. All right, so we go ahead and start integrating this, which is a really nice, easy integral, right? We've got the integral of 400 t dt and the integral of minus 800 t squared dt. So we've got ourselves that I hat is going to be equal to, well, we don't need the integral sign there anymore. We've got 400t is going to be 400t squared over 2, which is going to give us 200t squared. 200t squared. And then we've got minus the integral of 800t squared, which is going to be 800t cubed over 3, minus 800t cubed over 3. This is evaluated from 0 to 0.5 seconds, and yeah, we got a little I hat there. All right, so let us just evaluate this. We evaluate at t equals 0, we're going to get 0, great. We just want the final result here, so we evaluate this then at 0.5. So we've got 200 times 0.5 squared minus 800 divided by 3 times 0.5 cubed. That's all good. 16.667, we'll say. 16.667. I'm going to call this Newton seconds because it's the impulse. Newton seconds I hat. There is the overall impulse given to this 1.2 kilogram mass over that 0.5 second time interval. Fantastic. So there we go. We got a part A down. What about the part B? What is the object's change in momentum? Well, B, since we've already got what I is, we've got that I hat is equal to delta P hat, which is then equal to 16.667. We're going to call it now, call it now kilogram meters per second. You smart? I'll be okay. Kilogram meters per second. So The only difference is the unitization that we're using. I'm running out of juice. We'll switch to calculator. All right, so from this, we can go ahead and start figuring out what the object's final velocity is, right? So if we want the object's final velocity, we note, again, that delta p hat is equal to mv final hat minus mv initial hat, which has to be equal to our 16.667 kilogram meters per second I hat. The initial velocity was equal to 0. The initial is equal to 0 given in the problem. So we've got ourselves then the mv final hat is equal to 16.667 kilogram meters per second I hat, which then gives us the grand finale of v final hat being equal to 16.667 divided by 1.2, that's kilograms, that's kilogram meters per second I hat on top. And we got divided by 1.2 gives us 13.889. 13.889 meters per second I hat. Which looks like it'd probably be around 30 miles an hour or so, give or take. There we go. Got the final velocity of the object based upon looking at the impulse and the change in momentum. Lastly, we're asked what is the average force that acted on this? Well, the average force is the constant force ultimately that would produce the same effect. So we just want to know then, hey, what constant force would produce an impulse over 0.5 seconds of 16.667, or equivalently produce a change in momentum of 16.667 over that 0.5 second time interval. So we've got then the ability just to look at sigma, this is a part D, sigma F average times delta T is equal to 16.667 Newton seconds I hat. And what does that give us then? Well, we just say that sigma F average hat is going to be equal to our 16.667 Newton seconds I hat divided by the time interval of 0.5 seconds, which gives us 2 times that, that's fine, divided by 27.778. 27.778. 27.778 Newtons I hat. So a constant force of 27.778 Newtons acting over 0.5 seconds would produce the same ultimate change in momentum, which will result in this object having a final speed of 13.889 meters per second. That's pretty much that. All right, so constant, varying, doesn't matter. Impulse from the net force produces the object's change in momentum. It's good stuff. All right, that's it for now. We're going to come back and look at some more momentum momentarily. All right.